Good morning, everybody. Thanks for joining us for today's webinar. I'm Paul Gruber, the Executive Director of the Sustainable Transportation Energy Pathways Program, and we're very excited to present our analysis on natural gas by Amy Jaffe and Rosa Dominguez-Faus. And before we get started and I introduce our speakers, let's handle a few housekeeping issues. The format for today will be a 30-minute presentation followed by a 30-minute discussion. We really aim to have a good discussion with you all, and we encourage you to ask questions via the chat function in your on the ReadyTalk system. And we've muted everyone, but you can ask the questions via chat, and we wanted to let everybody know
the conference has been unmuted.
We're also recording the webinar, and we'll post the link to the PowerPoint slides and the webinar recording after we conclude the webinar today. The paper, Rosa and Amy are going to present some results from a recent white paper, Natural Gas in U.S. Trucking, that we recently released. And that paper is available for you online now on the STEPS website and on the Policy Institute website. And it should have been included in the link to the webinar invitation. So you can reference that as we go through the webinar today. And then again, after the webinar, we'll post the PowerPoint slides, we'll post the webinar recording, and you'll also receive an email with those links and a link to a survey that we encourage you to complete regarding today's webinar. So with those housekeeping issues handled, and again, an encouragement to use the chat function throughout the discussion. Oh, I'll mention, if you have clarifying questions, go ahead and let us know. We'll try to address those as we go through the PowerPoint, or as we go through the presentation. But for the most part, we will save in-depth questions for the discussion section in about 30 minutes. Okay, so now I'd like to introduce our two speakers. We're very lucky to have Amy and Rosa with us today to present this research. Amy Jaffe is the Executive Director of Energy and Sustainability for UC Davis. She holds a dual appointment at the Institute of Transportation Studies here and at the Graduate School of Management. And within the Institute of Transportation Studies STEPS program, she leads our fossil fuels research area. So she's an expert, a global expert on oil and gas. And as of this January, she's also leading a new 4-year project with us that's looking at the future of fuels and the oil and gas industry. So she's very well positioned to help us understand technological changes that could impact the fossil fuels industry. And then also Rosa Dominguez is a postdoctoral researcher here at the Institute of Transportation Studies, and she's very much Amy's right-hand woman, I'd say, doing a lot of the research analysis, and she's quickly becoming our go-to expert in GREET and LCA analysis and natural gas and trucks and a number of other items. So with that as a brief introduction, I'll turn it over to Amy, and we'll begin going through the presentation.
Thanks very much, Paul. So it's a pleasure to be here this morning to talk about the subject. The subject could not be more timely because we are in the middle of the winter, and natural gas prices fell below $3 per million BTU this week. And so raising people to ask the question, why are natural gas prices so low, even with oil prices being low, since natural gas prices continue to fall. I believe there's continued interest in natural gas as a transportation fuel, and we'll be talking about that today. So first, let me talk to you a little bit about the sort of price environment we're seeing in the United States. As you know, we've had this extended period of very high oil prices and for a period of time, very high natural gas prices in the early 2000s. And that led to a number of different market responses. One was it encouraged oil companies to try drilling innovations to unlock difficult resources, in the case of the United States, in the unconventional tight oil and shale gas space. And also at the same time, as you know, when we have high oil prices, that encourages conservation. It encourages energy efficiency technologies. We get substitution of fuels. Of course, that's coming up against the context of a pressing need to address climate change, which is encouraging big players like the state of California and the EU and others to try to push to lower carbon fuels. So you have this coagulation of factors where you're having companies able to, because of high prices, do much more innovative and experimental drilling technologies at the same time that you had a lot of demand destruction forces coming into the market, including the recession. And so what we saw, if you look at this chart that I have displayed there, you see the red lines. That is sort of the price trends and the context of those price trends in the 2000s overlaid against the black line, which is the cycle that we saw in the 1980s and 1990s. And I show two things by showing this slide. The first one is the idea that people had that we would somehow get out of the boom and bust cycle for oil and gas prices was incorrect. We haven't peaked geologically. There's plenty of oil and gas available. I can talk a little bit about the price environment of that. And so, it's just gravity in the market. Eventually, when you have more and more substitution come in, you have more and more efficiency come in, you have economic growth get slowed down because of the drag of high oil and gas prices, that takes away from demand at the same time that you have this increased supply that comes from innovation. We saw that in the 80s with offshore oil. We're now seeing it onshore with the unconventionals. And I do think it's possible, unless there's a giant change in the trends based on geopolitics. I do think it's possible, if you notice the black line, that there was an extended period of low prices after the price shocks in the 70s and early 80s, and I do think it's possible that we would see a similar thing, especially in natural gas in the United States. So one of the things that people ask about is, what's the break-even number? Why isn't the natural gas shutting in? Why do we continue to have such sustained low prices and continued supply at sustained low prices? And that is because not only, as I show in these charts, is the break-even cost for the unconventionals actually fairly low in many of the major basins, but also when people, look at their what I call sunk costs. In other words, I've had a drilling program somewhere and take the Marcellus, and those costs are sunk in their past. I've already leased the land, I've already done my permits, I've already paid all these costs, and so then I move to what I call my OPEX, which is what are my operating costs to continue to drill and to continue to produce. And the OPEX in the United States can be quite low. And in the Marcellus, there's some places where people say that actually the all-in costs are $1 in some developments, but for sure the operating costs are $1, which is still very low compared to today's price, which is somewhere between $2.75 and $3. So I think we're going to continue to have a lot of natural gas supply, and indeed, one of the interesting things is how diverse the geographic location is for the shale gas. And so some people have talked about, the sweet spot. Once we start drilling outside the sweet spot, there's going to be a huge decline in availability of supply, and that's not really my view. If you look at this map, you can see there's a lot of resources all around the United States and Canada and Mexico. We're a long way away from exhausting the sweet spot in all of those locations. The companies are seeing these huge productivity gains per well, some in the order of magnitude of 20 to 40% in the last year or so. And so when you see the rig count fall, part of the reason the rig count is falling is not because of the economics. Part of the reason the rig count is falling is because we need less rigs to do the same amount of production. So the interesting thing about the shale gas is that it lends itself to supply security because there's so many different parts of the United States where you could source supply. And therefore, it's not like, say, offshore where if there's a hurricane season and suddenly natural gas supplies get curtailed, there'd be a giant price spike. Because it's so diverse, there's a lot of security in that. And that, combined with the fact that prices are very low, has caused people to speculate about natural gas having a big role in the transportation sector. And the most excitement came about whether or not natural gas could be a major cleaner fuel for heavy-duty trucks, for Class 8 trucks. And so we created an optimization model to look at what would be the optimal supply chain for long-haul trucks, looking at different scenarios for either high diesel prices or for possible subsidies. There's some states that have given subsidies, like Oklahoma and Utah and Colorado. And so we were trying to get a sense of the policy environment and then how commercial and where it would be commercial to have this shift to natural gas, and whether the shift to natural gas would either A, have environmental benefits, or B, provide a good transition to cleaner, lower carbon fuels. So the optimistic forecast for natural gas moving into trucking came from the so-called S-curve experience of the shift to diesel fuel, and which did, happen slowly, and then all of a sudden the entire fleet went to diesel, and so people have questioned whether that could happen in natural gas. We did not find that to be an easy transition as people had imagined. Actually, what we found was that network development for LNG in trucks, and eventually we also looked at some CNG scenarios, which we are going to continue to work on. What we found actually is that that the development of the corridors for stations was very sensitive to travel intensity, and therefore, as you can see from this graphic, that the combination of higher diesel prices and also high volume traffic was most intense in California, in the Great Lakes area, and sort of in the East Coast Mid-Atlantic area. And therefore, when we did our studies, what we found was that that the current cost advantage is not sufficient to launch a national network on its own, but that actually the California corridor is quite commercial, and that over time the California corridor could be expected to spread beyond the state. The explanation for why it is that the cost advantage isn't sufficient to launch a whole national network is that when you look at the cost of diesel fuel, even though the cost of natural gas is so much lower, as indicated in the red bands in this graphic, the cost of the infrastructure amortized is so expensive compared to the already established network of diesel stations that in most locations it's just not going to return a commercial rate of return to build the stations in most locations in the United States, except in these corridors where we found a heavy volume of traffic. So the interesting conclusion, which is ironic since we're a California-based institution, was that actually California had a very unique commercial market that made it very attractive for natural gas trucking, and that's, I think, pretty easy to explain. California has one highway, I-5, where the vast majority of trucks have to travel. It makes it sort of like a railroad line where, the trucks, we know exactly where the stations have to go. There's a limited number of stations that would have to put in. California already, because of the commitment of the state back 10 years ago, because of air quality in Long Beach, made some investments already in natural gas fueling, and so it really lends itself to a network. And we did find that over time, as demand for alternative fuel trucking might rise, and as more trucks come onto the road, that the California network could indeed be the source of a national network, be sort of the first piloted route for a national network under certain conditions, that being that the spread between oil and gas be maintained at an attractive level. So it doesn't matter what the absolute prices are, it's the spread between the two. And then also to get the system going and started would take about twice as many natural gas vehicles as are on the road today in terms of heavy-duty trucks. And the view of this market is interesting because one of the great potentials for this system is that even if it began with fossil natural gas, there is a great possibility that the fossil natural gas would be able to be built at a 12% rate of return, some kind of pretty reasonable rate to investors. But eventually, that system could be used for biogas, and that would allow for a much greater environmental performance for the freight industry. But there are still some concerns in terms of the efficiency of vehicles and other kinds of environmental factors. And I'm going to turn over to Rosa Dominguez, who's going to discuss that briefly, though we will be having a full seminar on the environmental features because I think there's so much interest in that, and we want to be able to discuss that in more detail.
Thank you, Amy. Yes, so as I said, this is a primer on environmental analysis. We will discuss the methodology and the assumptions and sensitivities in another seminar. What I want to show here is the results of that I've obtained on the carbon intensity of natural gas vehicles as obtained by using the grid 1, so national grid, not California grid, and the 2014 version. And I chose to use this version because it's more up-to-date in terms of natural gas supply chain, the leakage in the natural gas supply chain, and also because it incorporates heavy-duty vehicle pathways, unlike any other previous version of grid or California grid. So it's a little more accurate in terms of representing these heavy-duty vehicles. So what I'm showing in this graph is the carbon intensity measured as grams of CO2 equivalents per mile. So this is not grams per megajoule. So it's not the carbon intensity of the fuel, it's the carbon intensity of transportation, right? It's once you use this fuel in the truck. And although natural gas has a lower carbon content than diesel, what we show is that because natural gas typically uses less efficient vehicles than diesel trucks, then all the benefits of switching to natural gas are not that clear, right? So there's a punctualization here. So natural gas can be used in spark ignition trucks or compressed ignition trucks. In the market, what dominates right now is spark ignition, which are a little less efficient than the traditional diesel compressed ignition engines. That will make a difference. Another difference is how you store natural gas. You have different supply chains for CNG and for LNG, and that means they use different parts of the distribution chain with different leakages, and they will also have different energy inputs. So emissions associated the fugitive emissions associated with natural methane leakage and also upstream CO2 emissions from these energy uses are different. So this graph shows diesel, CNG in a spark ignition combination, LNG in a spark ignition combination, and LNG in the HPDI model, which is a compressed ignition engine. The different colors represent the different stages of the well-to-wheel life cycle. So the gray colors show the pump-to-wheel emissions. So that's vehicle emissions. And what's interesting to see is that the majority of emissions come from this part, from burning the fuel in the truck, right? What the darker gray area and the lighter gray area shows is darker gray is CO2, lighter gray is the methane, because there is some combustion methane that can be found in the exhaust gas, and that's what's called methane slip. So if we go to the well-to-pump stage, which is the blue area and the orange area, blue is showing what we call the feedstock cycle. So feedstock procurement to the point where this feedstock is converted into a fuel. And then the orange is showing where this feedstock is converted into a fuel. So that's the fuel cycle. Again, the darker color is showing CO2, the lighter color is showing methane. So one of the things that we see here is the difference between CNG and LNG pathways. So where CNG has a higher feedstock, there's a larger contribution to the carbon intensity comes from the feedstock part, because natural gas in the CNG pathway uses more the pipeline distribution system, and therefore is more affected by the leakage. The LNG, the way we have simulated it, it's transported from the fields to the liquefaction plants via big transmission pipelines, and then it is liquefied in these central facilities, and then it is trucked to the refueling stations as LNG. So what that means, it is not using the local distribution system, therefore it's not incurring in leakage from this stage, and it uses more energy for liquefaction. Therefore, we see higher emissions associated with the fuel cycle rather than the feedstock cycle. So in summary, this slide shows that one thing. First, vehicle emissions are the major contributor. Therefore, any improvements in efficiencies or any differences in efficiencies will have a big impact on the overall carbon intensity of these transportation options. And the other thing is the difference between, so going back to that, so because a spark ignition engine is less efficient than a compressed ignition diesel engine, the spark ignition options are a little less favorable than when we use natural gas in a compressed ignition. This analysis is a little different than if we were comparing to gasoline applications, because gasoline is also spark ignition, so the lower efficient, and then this difference wouldn't be that important between natural gas and gasoline. And the second thing was just as a reminder, was the difference between the CNG and LNG pathways, which also affects the overall final carbon intensity. Another question that we ask is, so obviously natural gas is affected by methane leakage, to a more extent that oil fuels are, although they are also affected, but not so much. So what is the methane leakage throughout the supply chain, the overall methane leakage that we can afford in order to have a better performance climate performance by switching to natural gas? In other words, what is the break-even leakage rate, right? So we find that also depends on both the engine technology and the natural gas pathway, whether it is stored as CNG or LNG. And what I'm showing in this graph is the carbon intensity of the three different natural gas options and the diesel option, which is the dotted line, over different leakage rates. So that's testing the sensitivity of the carbon intensity of the different options to the leakage rate. And what we show here is two things. First of all, the orange line is CNG, the only CNG option we have running on spark ignition engines. Then the green line is LNG on spark ignition engines, and then the purple line is LNG on a compressed ignition engine. What we show first is that CNG is much more sensitive to an increase in leakage.
One clarifying question, what's on the y-axis, Rosa?
Oh, this is the carbon intensity. So it's CO2 equivalents per mile, grams of CO2 equivalents per mile.
Thanks.
And so what it is showing is that the CNG supply chain, the CNG pathway is much more sensitive to increases in leakage. So if we want to reduce the impact of, if we were to eliminate the leakage, in other words, or like any efforts put into eliminating the leakage will have a greater impact on the CNG pathway than on the LNG pathway. For LNG, it turns out it's not so sensitive to leakage because there's other carbon that dominate the carbon intensity, which is this upstream energy used in the liquefaction process. So any increase in efficiency of these processes could be a better sort of strategy in order to reduce the overall carbon intensity. What we find is using these spark ignition engines, there's basically no leakage rate. No break-even leakage rate is zero. So there's no leakage that we should tolerate. There's no benefit to switching to natural gas by using the spark ignition engine under basically any leakage rate. And that is the case for today's leakage rate, which we think is around 1.2%. However, if you use the more efficient HPDI natural gas engine, then a 3% leakage rate is what would be tolerable. That would be the break-even leakage rate. So it's very dependent on the storage type and on the engine type. And since this is a comparison to incumbent, it's very important to know that the incumbent here is diesel instead of gasoline. So this analysis will be different for gasoline. And I think that's what I wanted to say in terms of environmental analysis for today. Like I said, we are holding a complete different seminar that will talk about, this is a modeling effort, so lots of assumptions and lots of data that go into it, and we want to discuss, we want to justify why we assume one thing or another, and we also want to test the sensitivities. We also want to compare two results using the California grid, which will be different, and that will require more time, and that we'll do in the next session.
Yeah. And Rosa, before we conclude this part, another clarifying question: where are you calculating leakage in the natural gas system? Just at the production site or upstream as well?
It's throughout the supply chain. So we know where leakage is occurring based on, basically I'm using the EPA greenhouse gas inventory, and basically I'm using the grid default parameters, which are based on the EPA greenhouse gas inventory, and that includes leakage in the production, in the distribution, and it does not include leakage at the pump, and it does not include leakage at the vehicle. And my understanding is that there is a couple of research groups that are taking measurements. One is West Virginia University is measuring leakage at the vehicles and also tailpipe emissions. And then UC Irvine is measuring leakage at the pump. So once we have these new data, which so far just doesn't exist, we will incorporate this new data and we will see where it changes. And there's caveats to any modeling effort, right? So I have the impression that the model is a little biased towards diesel because it does not incorporate all the emissions that happen in the old pathways. For example, there is not a pathway for shale oil in the grid yet. And we know that shale oil development in North Dakota is producing a lot of associated gas that is being flared or leaked to some extent. So these emissions are not taken into account. And once we have these, the results will change slightly. And the other thing is that why I think these results are still valid, even though these caveats. One thing is that we know that some pathway, the LNG pathway is not as affected by this leakage. The other one is that the assumptions in the model are already pretty low leakage. And the other thing is that even though there's flaring and leakage in these North Dakota fields, this is something that at some point it will be contained. So basically, we also want to evaluate this situation.
Okay, so I'm looking at some of the submitted questions, and so I want to discuss a little bit about the prices that we use to do the modeling. So
first, do you want to address the last two slides?
Oh, I'm sorry, yes. Before I do that, let me just acknowledge the excellent research that went into this work and our co-researchers from ITS Davis and Arizona State, and also thank the support we received from GE Eco-Imagination, Westport, and Shell, that helped us with this project, and of course the entire STEPS consortium. We've presented this research several times at STEPS conferences and got some very good input from Department of Transportation and other agencies and other corporate specialists, so we thank everybody for their input. To sort of give an overview of what we think the takeaways from this research are, one is that whereas the alternative fuels cost discount compared to incumbent fuels is important, it's not the only element that makes for a successful transition to a fuel or a low carbon fuel. Because you really have to look at the cost of new infrastructure in how a new network for fueling is going to be developed. And I think that was sort of one of the surprising results of the research. One might have imagined at the time, because natural gas presented this large discount on a diesel gallon basis of between $1 and between $1.50 and $2. One would have just thought the computer would build stations all over the place because it would be so profitable. But then the cost of having to build new infrastructure is actually a pretty big barrier. And as I discussed, the traffic volume is a much more important element to the infrastructure success than natural gas surplus. And what do I mean by that? I'm sure there are a lot of players that think that the best place to start with these stations would be, in and around the Marcellus gas in Pennsylvania or in Texas, where there's a lot of gas, or North Dakota where you have flaring. But what our research shows is that really a much more important element to having a successful transition to this different fuel has to do with where is the high volume of traffic for the trucking industry. It's a much bigger variable. And therefore, we feel like this sort of corridor approach that was once discussed by DOE for biofuels, that the corridor approach is probably a better policy strategy if one wants to launch alternative fuels, and certainly in natural gas, than trying to make a national market. We also found that some of the new technologies for fueling, such as modular small-scale LNG, is still too expensive to stand on its own without some kind of government subsidy or some kind of technological breakthrough that would lower costs. And that there are technologies, as Rosa discussed, in the trucking industry that really can be deployed and invested in that could make natural gas a much better performer as a fuel, but that maybe that would take some additional government regulation.
Okay, great. Thanks, Amy and Rosa. So questions are coming in, some of which are fairly technical. We'll try and very related to GREET. We'll try to address all of these that we can in the time given. For some of the more technical ones, we'll try to get to them today. If we don't get to your question, we've got a nice log here, and I encourage folks to reach out to Amy and Rosa directly, and we'll also try to reach out to folks that have asked these questions. So first, and let me also say we won't be attributing questions to you as individuals. So don't hesitate to continue to ask questions. We're just going to be responding to these, and we won't be attributing them to you. So first, just a clarifying question on the price spread used to do the modeling.
Right, and let me also say on the details of the environmental modeling, we are going to have a separate webinar on that topic. So if we don't get to your question today, do know that you can dial in at the next webinar, and we'll definitely get to it at the next webinar.
Right.
So when we began our mission of doing this modeling, we used the GIS data and the diesel price that was available across the United States. If the person who's interested in that is interested, we can definitely, in the paper, I do believe, in a longer version of the paper somewhere, there is actually a table with all the different prices. But roughly speaking, the spread on a diesel gallon basis was about $1.50 to $1.75. Maybe at the time we did the modeling, the diesel price was probably around $3.75 to $4 across the United States. We used the actual forward curve for the NYMEX for natural gas prices, so the actual Henry Hub futures curve is how we priced the natural gas, and then we did the specific prices at the hubs, and again, in a longer version of the paper, there's some material on what hubs we picked. And so I would say, generally speaking, the price of natural gas at the time we did this study was probably around $3 per million BTU at Henry Hub, and the forward curve, discounted that out a little bit. So those would be where the prices were at the time. We have a question about how it changes if there are several fleets, say UPS or some other, Walmart or other major players switch to LNG. So obviously, the more players that switch to LNG, then the more realistic and more commercial the network becomes. So we found that it would take so we are now, the penetration in the market of LNG trucks is about 0.01%, and it would take something like 3% penetration for there to be a really prolific national network.
We've got a somewhat technical question regarding GREET, so this one will go to Rosa.
Mm-hmm.
What's the global warming potential for CH4 that was used in the modeling? Can you speak to that a little bit? And if the 100-year value was used, there's a question regarding whether the 20-year value would be more appropriate.
Yeah. So no, it was we used the 100-year value, and whether the 20 or 100-year value is more appropriate, that's very discussed. I mean, it really depends on whether you're looking at the short-term or long-term impact. And what some people have proposed is that it really depends on when peak warming is going to happen, because basically you're having like a short-term addition that will go down. It will go down also faster because methane is a short-lived pollutant. So whether you're doing this additional temperature increase in the first part of the century, in the first half of the century versus if it happens in the second half of the century, when this peak warming is believed to occur, it's a big difference. Basically, you're adding on a low baseline or adding on a high baseline, right? So I don't have an opinion on that. I'm using the 100-year global warming potential because that's what that's customary. That's what IPCC recommends. I'm using the value of 30 instead of 25, so it's a little less favorable for natural gas in that case because I'm weighting methane more than previous studies. And there's a proposal that we should be using 37 instead of 30, but this is still being discussed in the scientific forums. So yes, we've used the 100 potential, the 100-year potential, and then we're using a 30 value for that instead of 25.
Okay, another question here. In this analysis, do we incorporate methane leakage associated with the extraction of petroleum from which the diesel fuel is refined?
Yes. So like I said, the grid model does not incorporate a pathway for shale oil, and that's where most of the methane is being either vented. That's when more of where the associated gas that's not wanted is produced. If there is associated gas that's wanted, then people put it in the pipeline and sell it. But since most of this shale oil development is happening in North Dakota and there is not an infrastructure or an interest, given low natural gas prices, to monetize this associated natural gas, then what they do is either vent it or flay it. So that's where more the big chunk of the emissions, these fugitive emissions, happen in the old pathway, and that's not incorporated in the grid yet. So I think I've mentioned that caveat that, you know, at this point, grid is a little biased towards oil. But in the future, we expect all of these emissions to be contained. So in a way, we're simulating a future scenario.
Okay. For the diesel carbon intensity, did we use California-specific values for crude oil supply and refinery emissions, or did we use default crude supply and refinery values from GREET 2014?
Yeah, I use the defaults because this is more of a national study. I'm using national averages for everything.
Okay. Another question on carbon intensity. So on slide 11, I think it's actually not slide 11.
That must be slide
13?
Slide 13.
Slide 13, yeah. The approximate carbon intensity was 90 grams CO2 per megajoule. Can we explain why the carbon intensity seems to be low compared to the LCFS regulation at 102 grams CO2 per megajoule?
The approximate carbon intensity of natural gas, I assume, and so mine would be 90. I'm not sure I understand the question. So, okay, one thing is that you are showing the, maybe that person wants to reformulate the question to specify.
I think it's the difference between grams versus
Yeah, so
miles.
one thing is that, right? So first of all, the LCFS talks about the carbon intensity of the fuel. It's low carbon fuel standard, right? So you want lower emissions in the fuel, right? But when you convert this metric into grams per mile by incorporating the fuel efficiency of the vehicle, then you are also taking into account not only the carbon content of the fuel, but also the efficiency of the vehicle, which in this case it's critical because we are comparing lower efficiency natural vehicles to high efficiency diesel vehicles. If you were comparing low efficiency natural vehicles to low efficiency gasoline vehicles, the difference wouldn't be so big. This phenomenon wouldn't be as important.
Okay, so from our analysis so far and pending work, I have to say, what do we think the impact of using methane from biogas could be for the environmental impact of use of natural gas in transportation?
Yeah. So biogas would reduce considerably the carbon intensity of NGVs because basically you have a negative carbon intensity in biogas. In other words, you get carbon credits because if you're not producing this biogas and burning it, this biogas is happening in the landfill, I mean, in case of landfill gas, and then it's being emitted. So by containing these fugitive emissions and putting them to some use, you are basically gaining carbon credits. Burning the biogas in the vehicle will emit the same carbon as burning natural gas, but because in the upstream you're doing this good thing, which is containing the emissions that would otherwise happen, then overall you have a lower. I don't think you have a completely negative carbon intensity, but you will have a much lower.
Well, because you're still going to have methane leakage from the pipeline distribution.
You're still going to have methane leakage, and then you're still going to have emissions from the vehicle. So the net carbon intensity would still be a little positive, but it will be much smaller than what we see now. So a natural gas engine using biogas would be better than a diesel engine, basically.
Okay, got another good question here. Why did we focus our analysis on commercial vehicles? Why didn't we look at light-duty natural gas in light-duty vehicles? And there's a point here, or a question: wouldn't that lead to certain economies of scale if you can deploy a wider infrastructure for natural gas use?
So we had several reasons for that. The first one, and let me just say that there is sort of better environmental performance of natural gas in buses and some other smaller vehicles. The life cycle analysis is a little more favorable than in the commercial vehicles. But in terms of the payback time for the vehicles, to have the vehicles pay back, you need to travel a certain number of miles a year, and really only the commercial fleets have that much travel per year. And so that's why we focus first and foremost on vehicles that go more than 120,000 miles a year, which takes you to Class 8 trucking. And also, I think in the sort of light-duty space, there are many different alternatives because you have hydrogen vehicles and you have plug-in electrics and you have hybrid vehicles. Also, the LCA for natural gas is more positive when you compare it against gasoline versus diesel because diesel technologies like direct injection tend to be very, very efficient. So we started with the areas that we thought had the most potential to eliminate oil, and looked at that first.
Okay, thanks. A couple other questions here about the maximum leakage rate we looked at, which was 10% on this slide.
Yeah, so this is basically a sensitivity analysis. So we're not saying that's the leakage rate. We're just saying if that were the leakage rate, then what would happen? Now, having said that, we have reviewed all the existing literature in methane leakage, and although I think that leakage is under 3%, is realistically under 3%, some authors have found higher leakage rates up to 8 or 9%. So that's why I'm including this range. Now, to talk a little more about that, I think what the literature is finding, what the scientific studies are finding is that there is some occasions in which there might be this high leakage rate. There is a small number of operators that contribute to the majority of leakage, but on average, the leakage rate is much, much more below that high number. So the official estimate is around 1.2%, and then a sort of meta-analysis of the published literature that basically try to harmonize the different assumptions that went and methodologies that went into the different studies found that it is more likely that the actual leakage rate is somewhere in between 1 and so almost 2 to 3%. That would be like, and then that is the reason. So why the actual leakage rate is so different from what the EPA inventory tells us? That's because I think two things. The EPA is not taking into consideration these big polluters, and then the second thing is that there are some emissions from abandoned wells that are not incorporated into the inventory too. So, but I'm in here. It's a sensitivity analysis. I'm just providing a range. I'm not saying 10% is the leakage rate. I actually think leakage rate is between 2 and 3 at most.
So I'm getting a clarification question on why we picked heavy trucks first. So I'm not saying that there aren't other vehicles that have a good rate of return. Obviously, across the entire class, companies are experiencing a good rate of return, shifting to natural gas in terms of just basically cost and price. I'm just saying that in terms of developing an entire network of stations, what we found was that these vehicles that travel the greater distances were going to be getting a faster payback, and thereby more likely to be supporting a development of a national network. We have a couple other questions on the infrastructure questions. For the I-5 corridor, we found that the cost to launch that infrastructure was below $100 million. So actually pretty economical in terms of the amount of investment needed, and that would also be supplemented by the existence of private and public stations that are already involved in the state in CNG and other kinds of natural gas fueling. We had another question about where we might think the shale revolution will go next. And I wasn't sure if people are asking next in the United States or next outside the United States. So what I would say to that is that outside of the United States, I think the big Mexico is going to be the next big potential. There, we have the energy reforms coming in Mexico. So I would expect that there will be a lot of potential there. The companies have had some actually good initial success in Argentina, and so there's some geopolitical risk and government regulation in Argentina that probably needs to be negotiated that might make that potential more attractive, but geologically, Argentina is considered very promising.
Yeah. In general, they say there's a few criteria that are met in the U.S., but not all of those are met outside the U.S. For example, one is geologic, the other is a technical expertise and a competitive industry that does more innovation. And another criteria, for example, is land ownership. In a lot of other countries, farmers don't own the land, don't own the mineral lands of their lands, unlike here. So at a private level, people will not reach the benefits of, producing these shale resources. So I think from the point of view of social acceptance, it's not going to happen like it's happening in the U.S., where a lot of people can make a lot of money by selling their mineral rights. In other places, people don't own the mineral rights.
So in thinking about other environmental impacts, we had a question about water, and what I would say is that there is a problem with water issues in different locations. Some of that's very location specific.
Yeah. So water, we typically distinguish between consumption of water and pollution of water. So what we're finding is that water for fracking, typically to frack a well you need about 4 million gallons of water. And that seems like a lot of water, but then you have to think that wells are fracked only during, an initial period, and then they keep producing, although they might have workovers, but they keep producing for a long while. And they are typically more productive than typical natural gas wells. Therefore, the water intensity of shale gas could be even lower than regular gas, because although you're using more water, because you are also producing more natural gas. I think what we find is that water consumption is not going to be a big problem overall, other than in specific regions that have water constraints already. And water is always a contentious issue between the different users. So in that sense, I don't think shale development is any different than other uses of water. Now, we have the problem of water pollution. When you frack a well, you use this water that most of it comes up, well, maybe 60% of it comes back as flow back water. And this is water that contains sand and chemicals. And then this water, although the industry contends that the chemicals are not more toxic than some domestic products, you still have to treat them. The other type of water that you have is produced water, which is water that was in the formation. And that's typically water with high density of salt, high concentration of salt. And, it might have radioactive materials that were naturally occurring in the formation. And so you have these two different types of water, and, it's hard to distinguish when you're transitioning from one to the other. But nevertheless, these two waters need to be contained. And so it really depends on the regulation of each state that the way they treat these waters. So you can have them, you can store them in open pits. We know there's been some poor practices of how to manage this water, but there can be good ways to treat them and make this water available. And then you can always, and the industry has an incentive to do this, reduce the amount of water that you are using. Now, for the produced water, it might not be, so that happens in the U.S. when some water is not technically or, economically possible to treat. What they do is inject it in deep wells. And that's not oil and gas only, that's, nuclear waterways, that's sometimes municipal, some other industrial ways. And those are deep injection wells that are regulated by the EPA. And these injection wells will put this wastewater deep down in the soil, sometimes hundreds of feet below any freshwater aquifer. So I think the risks of pollution from these disposal wells is low. Now, if the water that is not disposed in those injection wells and is treated on the surface, is managed on the surface, is poorly managed, then you can have infiltrations to the aquifers. So I think that's a little bit of a summary of what the water issues are that's coming up in another study. Actually, it's not part of this study.
Okay, well, I want to thank Amy and Rosa for their time in walking through the natural gas issue, and thank you all for joining us on today's webinar. We got through most all the questions. There were a couple more that we noted, and we'll follow up with folks. And if you have follow-up questions, anybody on the phone, feel free to reach out via the webinar email link, and we'll direct the questions to Amy or Rosa, or you can reach out directly to them. And then the next webinar, which will focus even more on the environmental impacts, we'll be sending the invitation for that here shortly. It's likely to occur in the next 2 or 3 weeks. So if you're not signed up for the email list, go ahead and sign up via the Policy Institute website, and we'll keep you apprised of that. And thank you very much, everyone, for your time today. Bye-bye.